All right, I'm going to start. Welcome to the closing speech of the NDC this year. We're gonna try to sum up everything. Now, this is the low power cellular for the IoT. I'm going to talk about some interesting new opportunities that are coming along from new technologies that are brought into cellular that come from the low power, low throughput aspects that are needed for cellular connecting everything in the IoT. So who am I? My background is in technologies. I started doing software, and then I kind of wondered how these things work, and I ended up starting to work on hardware, designed a microcontroller core that was used for processing on radios. That led me into working on this wireless system on chips. I've been doing that ever since, really, and working on the architecture of these processing and wireless communication silicon chips that go into the IoT. And consequently also working on the software that runs on them, both from a stack perspective, but also the application. And I also do a lot of work on snow shoveling, of course. That's mandatory in Norway. So my name is Peder Rand. I work for Nordic Semiconductor. And we make, among other things, these wireless SoCs. So cellular IoT, why does it matter? I think one of the reasons, so there are always new standards that come about in the wireless space. One of the things that makes a cellular IoT especially interesting is that sort of the network is already deployed. And then they come up with the standard. So the 4G routers, base stations, are already out there. They're deployed out. We have great coverage in most countries in the world, and then along comes a standard that makes it possible through a software upgrade to make these base stations talk to low-power IoT devices. So that's what makes it interesting. It's not a slow rollout. It's quite fast. And from a couple of years ago, there being nothing, till now, it's kind of everywhere. It's an interesting journey. And that makes it very interesting to look at and something that can scale pretty quickly. And there's some interesting applications too. So this is about, removing the gateway. Because the gateway as a sort of privately owned unit in a network is just a nuisance. It's something you need to have there in order to make everything work and actually talk to the cloud. But it doesn't really do anything for your product, which is your IoT device that you're shipping out to the customer and provides the service. So what you actually want to do is go directly from your IoT device to the cloud, to someone else's computer, which is the cloud. And I count the cellular network in the cloud because it's someone else's computer. Someone else's problem to make sure it works, and it's professionally managed. And it's always there, and it's had a great coverage in the industrial world. So, and as we all know, budget-wise, I think we just made this whole solution a lot cheaper. We removed the $1,000 iPhone, right? So what can we use it for? A big one is asset tracking. You go on Google for everything now and search. You expect to find everything there. And it's kind of amazing that you can't really find your things on Google. So if you lost something, you can't find it there. But that's about to change. You should be able to go on, Google or whatever other platform you have for cloud and find your things. And the reason why this is a good fit for asset tracking is because you can get the location, GPS signals coming in to sometimes the same piece of silicon that runs the cellular network. You can get the condition by interfacing to a sensor like temperature, humidity, measuring shock, for example. You can also communicate to subunits using a short-range network. If you have, a container like this, you may have pallets inside or boxes that you track with smaller units, like Bluetooth Low Energy or similar. And I think the appetite especially for companies and industrial companies to know at any given time where all their things are, the things that they own, and they may be valuable, and it may be very expensive to have people running around to look for them. That is something that is slowly being acknowledged more and more. And the fact that you can now do it using the same cellular network that you're using with your phone and have devices, small as this one, running on a battery, tagged onto it, stick there, stays there for 2-3 years without changing the battery, and you know at any given point in time where it is and what condition it's in. You have healthcare. And that's a completely different dynamic. But that's really an aspect where you don't want the patient to be the network operator. What I mean by that is it's extremely important to reduce the amount of time that someone needs to spend in the healthcare institution, like a hospital. So if you can send them home a day early, a couple of weeks early even, and doing that safely by making sure that you can still monitor their health condition when they're at home, that can save the society a lot of money. And it makes for healthier and more happy people and patients. So the problem with that is if you send them home and say, hey, connect this thing to your Wi-Fi network, and we should be able to monitor you as long as you stay in your house. It doesn't work, right? They have to punch in the SSID somehow, and the chance of it failing is just extremely high. The thing is, with a cellular network, when the patient leaves the hospital, the thing's already working, it's connected. When they are out on the street, it's connected. When they get home, it's still connected. And the patient doesn't have to think about it or do anything. And that's extremely important. Wearables. There are scenarios, everyone has these smartwatches these days and connect them to their phone, etc. But there are cases where you kind of want to leave the phone at home. And actually not carrying the phone anywhere is something that some people appreciate as well. Especially in the sport and fitness and sort of security and safety, there are aspects of that you may want to be able to send a message to the world, but you don't really want your Facebook on when you're out running. So that is an interesting aspect. Maybe more useful overall for society is the metering. In countries like Norway and most of the developed world, and actually now in parts of the underdeveloped world as well, they're deploying meters and infrastructure for meters that are automatically read. And the infrastructure is generally sub 1 gigahertz, proprietary networks that they put up masts, they put up gateways, they communicate with a proprietary network to the stations that they can see, and the meters that they can see, and then they communicate that back to the cloud through the cellular network. That can be simplified a lot by just connecting every single meter to the cellular network now that the cellular devices have gotten smaller, less complex, draw less power, cost less, and it gives great coverage and scalability. The LTE networks are really fantastic. Remember in the old days when, if there were a lot of people around, maybe you couldn't even place a call. If you're at a concert or something, you couldn't do anything. But with the LTE, there's like almost limitless how many nodes you can have in a certain area by well-managed network planning. And then smart city. Cities can save a lot if garbage truck routes by knowing where in the city the bins are full. So if you can at any given point in time feed an algorithm all the information about where the trash is, you can optimize the routes quite significantly. Have less trucks. The street lights can be on only when they need to. You can have share bikes that you can find easily on the map on your phone. Go pick one up, take it to wherever you want, drop it off again, and someone else can find it there. Smart parking. So in the cities, there's a big problem with people driving around the block several times to find a parking spot. It increases traffic a lot and annoyance as well. And smart parking is about being able to reserve a spot for you near where you're going and knowing that it's there and available when you get there. Using sensors in the ground mostly. And there are all these other ones like predictive maintenance, products as a service, placing a product in someone's home or business and not charging for the product itself, but charging for the service of using it, making sure that you maintain that connection. But what we're really hoping is that the biggest applications for this and the things that will really change things is not on this slide. It's something that we haven't even thought about yet, that someone is working on in the garage somewhere. So where do we place the low-power cellular IoT in the landscape of different low-power wide area network technologies? So I like to categorize it into low power and not so low power standards, and then by throughput. So if you look at, this is your traditional cellular that you use in your phone, like LTE category 6 or 9, not at all low power, but very high throughput, fantastic efficiency, but doesn't really work for devices with low throughput. And they have 2G, which was a great idea like 25 years ago, but it's very high power and not very spectrum efficient. And then comes NB-IoT and LTE-M as 2 standards. They're a bit different. I'll talk about how they're different, but they both basically serve to replace different aspects of the 2G functionality while doing it at a very low power and being future-proof. As we all know, 2G is going away. 3G is going away even faster than that. The spectrum that is used for those technologies is too valuable to use for old technologies like 2G and 3G. So I think in most regions of the world, 2G will be gone by 2025. And if you're placing a product in the field now that's supposed to last for 10 years, simple math, that won't work. You'll have to come up with something else. So one alternative is the proprietary low-power wide area networks, like Sigfox and LoRa and some of the other ones that was shown earlier today as well. To compare the two, there's licensed and unlicensed bands. Cellular is in licensed bands, which means the cellular operator paid probably a lot of money to be able to be the only one to operate in that band, which means there's no interference from anything else operating there. And when you then have an advanced protocol like LTE on top to make sure that the individual devices that operate in the network don't step on each other's toes, then you have what is a great scalable solution with good quality of service. Security is built into LTE from day one. We all know the SIM card, right? That's what it is. It's an authentication and encryption piece of hardware that makes sure that when you connect to the network, it knows that it's you. It also knows the secret key, so you can talk without being monitored. And having this security on board means you can connect also directly to your cloud service. So you don't have to go through some intermediate server that someone else owns. You can connect your IoT end device directly to the cloud and use technologies like TLS to secure that end-to-end. I'll talk more about that too. And then another one that's interesting, and for those of you who caught Joachim's talk earlier, there are no limiting regulatory restrictions on output power in the licensed bands. The licensed bands, you can use very high output power if you want. And in cellular IoT, you can use up to 23 dBm, which means you can transmit over very long distances. And you can transmit as much as you want within what the cellular operator will allow you. But for example, under ETSI for the sub 1 gigahertz 868 megahertz band, if you are not in a licensed band, but then in that public band, then you are allowed less than 1% duty cycle on transmit, which means that you're basically staying quiet most of the time to be compliant with the regulatory standards. So I mentioned both LTE-M and narrowband IoT. So what's the difference? It has to do with the link budget that translates into range traded off with throughput. So the LTE-M is higher throughput, up to 375 kilobits per second, but only about 4 times the range of standard LTE. Whereas NB-IoT is like 60 kilobits per second and can get you up to 7 times the range of standard LTE. And that's probably the biggest difference. And then we get into mobility, which means as you're moving down the highway, for example, on a truck, can you elegantly jump from one base station to the next and know which frequencies you should go to, et cetera, and being handed over. And you can do that now with LTE-M, NB-IoT. There's a future version that will support that, but doesn't support that yet. Can you do roaming, going across country borders and to a different network on a different operator and still have it work? We're so spoiled with that on our phones now, right? We get off the plane anywhere and turn it on, it works. But it's not automatic, and it doesn't work yet for NB-IoT. They have made it work for LTE-M because it's more similar to standard LTE. So I think at a high level, if you have a stationary node that's sitting there, let's say a smart meter, for example, talking to the same base station day in and day out with very limited data, then NB-IoT is probably the right choice. It has longer range and slightly less overhead on transmission, so it's lower power. If you have something that's moving around, that you're tracking, that may even cross borders, then LTE-M is probably the right choice. So I pulled this from the GSMA website yesterday. This is the current national deployment map for LTE-M and narrowband IoT. They update this very frequently. There are about 60 networks available globally today with LTE-M or narrowband IoT. Most of them are regional. Like Sweden is not as backwards as it may look on this map. They do actually have quite a few places where there is coverage, but they haven't deployed the entire country yet. And so this is, as time moves on, we'll see a lot more of these regions becoming purple. And, obviously they started in the Netherlands, where you only need like one base station to cover the entire country if you have it high up on a mast. But Norway is actually an interesting one because it's not a very simple geographic region, and they still make it work very well. So there's coverage all over the place around. So what are these devices that make up the IoT for cellular? How do they look? So essentially they consist of a few sort of components that are common to most wireless technologies. So you have your battery or your power source. You have some kind of sensor that's interfacing with the real world, reading temperature, humidity, acceleration, etc. You have your SIM card, or UICC, as it's called if you get very technical, that provides the authentication onto the network. And then you have the antenna. And inside of here, you have a processing unit, a modem for the RF, and some front-end components like amplification and things to make sure that you get the good signal out. From a software perspective, what's most interesting is this MCU that's sitting on here. That is what processes the data that's coming in through the sensor and decides what to send over the air to communicate back to the cloud. And that's where I would say the most of the magic happens when you decide to define a new device. If you're making a new product, you'll make some new hardware, sure, but that's not really where the magic happens. It happens in here when you decide what is the device actually supposed to be doing, what kind of data will it send, and how does it process that before it gets sent. From my perspective, working on designing these chips, the real magic happens here in the modem. there are millions of lines of code to make sure that the interaction between different devices in the cellular network is constructive and that they don't step on each other's toes, and you get all the throughput and quality of service that you need. So from an application perspective, what are you looking at, right? You put your application on top. Your interfaces to the network, you can choose from any of the standard protocols. MQTT is very popular, very simple. CoAP, HTTP, all pretty well known. They use an API, talk to the TCP UDP stack and encrypt with TLS or DTLS as appropriate through IPv4 or IPv6, depending on network support, and then down to the layers of the LTE stack into the physical layer that actually transmits the data to the base station. So in the choice of these application level protocols, you have MQTT, which is an ASCII-based machine-to-machine protocol. It uses a publish-subscribe model, so you can publish to a certain topic or subscribe to the topic and receive the messages. Typically, it runs over TCP and then uses TLS encryption. Now, this is a pretty heavy protocol for a constrained device, which is why they came up with the constrained application protocol as an alternative. And that uses a REST model like HTTP, like get, put, post, delete. It uses a very compressed 4-byte binary header and transmits over UDP, so you don't have the overhead of TCP, and uses DTLS, which is significantly lighter than TLS. Most silicon has acceleration for the encryption, so it's not really a big concern from a power perspective. This encryption, if you do it sequentially, processing-wise, it can draw a lot of power over time, but most silicon has acceleration that does the encryption in parallel using dedicated hardware blocks. But it still is it adds protocol overhead to use TLS over DTLS. So why not always use CoAP, right? Because MQTT is a lot simpler. And you can put anything in there. Like it's really easy to put like JSON payload into an MQTT packet, for example, and get that directly to the cloud. And it's easy, and TCP gets through all the firewalls, or all at least, compared to UDP, which you can run into trouble sometimes with some of the firewalls. So I guess those are the main considerations there. And then on top of that, you have your tie-in, I would say, with the cellular standard. So with MQTT, generally it's used with LTE-M, and CoAP is generally used with NB-IoT. So when you find reference designs, for example, typically that's what you'll find. But there's no real reason not to. You can mix and match. There's no. So I want to talk a little bit about the basics of LTE. How do you actually get a device onto the network? Because it's not your network. When it's your network, it's easy. When it's someone else's network, it's a little bit more complicated. I'm going to walk you through that. So here's your device over here. You've got your wireless SoC, your antenna, your SIM card. And then you have two base stations nearby, transmitting the master information block. Contains information about what kind of features it supports. Obviously, you can read the signal strength from it. And in this case, the device will scan and find both of these, and it'll see that this one is closer, has a higher signal strength. I'll connect to that one. It supports all the features I want. So it sends an attached request. That attached request goes to the mobility management entity, and then it sends out an authentication request to the device. Say, okay, so who are you? And that information goes back through the mobility management entity and all the way back to your home subscriber server. Now, I've drawn this in as a very separate entity because it very well may be in a completely different part of the world. Say you're roaming into some area in the US, for example. The mobility management entity is right there with the cellular core network of the operator that you're on. But this one is like Telenor or Telia in Norway that needs to be contacted to make sure that this SIM card is actually enabled with a subscription that allows it to roam here. And then once that's been confirmed, then you get a scheduler that schedules your time on the air, that allows you to get through to a serving gateway. This is in the core network of the cellular operator. And that serving gateway, or APN, allows you to get out to the internet to your cloud. And then you have your data flow from device through the, device through the serving gateway into the cloud. Simplified, that looks a little bit like this. So you have your cellular core network all the way to the cloud. And you can imagine, this is now, like from an IoT perspective, connectivity-wise, it's problem solved, right? You have your device, you have your cloud connection, you can get anything uploaded, downloaded, you're done. All you need to do now is write the application there, and you need to write the application on the cloud, and the connectivity is no longer a problem. But of course, you do need to consider security. So some of it's given. Like I said, security is kind of built into LTE, which is great. But so I tried to draw a tunnel here, but so the SIM card authentication and encryption actually allows you really good encryption over the air. So that gets you into the cellular core network. But you're going to go all the way to the cloud, which means you need another layer of encryption because this stuff's going over the internet. Once you pass through the APN, you're on the World Wide Web, right? So you need the authentication and encryption from your cloud to make sure that from an application perspective, it's talking to the right device, it's getting the data, and no one else is being able to see it. So it needs to be encrypted actually twice. But then, NB-IoT especially, this is a kind of popular model. It is, you have your device. It doesn't do any encryption other than the encryption that's assisted by the SIM card. And it talks to a server inside the core network. This may be a SCEF or a different type of server, but it talks to a server that sits inside of the operator's network, behind all the firewalls, right? And then you, from your cloud, you can get a token to go use an API that extracts data from this server inside the cloud. So then you're actually only encrypting your data once, and the encryption to your cloud happens in the second stage when it leaves the core network of the operator. So kind of the problem, I would say, with this model is that right here, this data is unencrypted. And it's your data, but that's not your server. And you can argue that the cloud is always someone else's machine, right? But it's still something that needs to be taken into account. What if you're roaming? What if this is in some operator's network that you don't even trust? So there are potential issues here. But there's a simple model, and then there's this. And this has less overhead. This is why it's popular. And will be the right solution for some, but won't be the right solution for all applications. And then flexibility and upgrades. And this kind of goes for all wireless technologies in the IoT, but especially important to think about when you deploy something in a wide area network. Because of its nature, the units are either far away or mobile, not easy to get to after you actually deployed them. So if you have 10 years of battery life as a goal, when do you find a bug? Probably going to find most of the bugs in the first 6 months. Probably going to have an appetite to fix those bugs and send out a new firmware image. And when will you find the security vulnerability? Hopefully before it becomes a real problem, right? But you may see the vulnerability, may want to fix it, maybe put a new version of the stack into the device. that should be done. And when would you want to upgrade your performance or features? Like if you deploy something and it's not really competitive after a few years and you're providing it as a service, then it's not good to be stuck with the kind of functionality of the device that's in the field. You may do like Tesla is doing. You may sell a car with all the promises of those great features that it's going to have sometime in the future. You sell the hardware, and then you start pushing updates to enable some of the features in the future. So the other aspect is when we're talking about machine learning and adaptive algorithms, and there's a lot of ways where this actually relies on updating the code that runs on the end device. So yeah, you need to use data crunching in the cloud to improve the algorithms, and then you need to push the algorithms back down into the devices so that they can make intelligent local decisions. I'll talk more about that. But basically what we have is a new standard, well, say new, it's a few years old, but from the Open Mobile Alliance, they've designed the LWM2M, runs on top of CoAP, and it has methods for transmitting new signed and encrypted firmware images down to the device. And the signed and encrypted is, of course, very important because you want to be absolutely sure that the device will only accept the firmware image that you want it to have. That no one else can actually update that. But once you have the cloud connection, this can be the same cloud as you use for your data and processing and application. Or it can be a different cloud provider that you use only for firmware updates, and that would go through a different channel. So I want to talk a little bit about embedded development, because that's, like I said, the magic happens when you implement the application on top of the stack inside of the IoT device. So some of the challenges compared to computers. The target device doesn't have a screen or a keyboard. How do you debug it? How do you step through the code and understand where it goes wrong? Because it will. It's a big challenge. I'll show that. Restricted data and program memory. These things they don't have more memory than they absolutely need to. And the reason for that is, 1 megabyte of flash to or fro may not mean a whole lot when you're buying a computer. But if you're going to build, 100 million toothbrushes with IoT inside, once you start multiplying that cost of maybe 20 cents for a megabyte of flash, you multiply that by 100 million, and all of a sudden, you are really eager to reduce the amount of flash that you use. And then there's a limited energy source available. Generally, these devices supposedly are mobile and last for a long time, so you can't just waste energy. Everything you need to do needs to be optimized. And you don't have cooling problems like you do in a data center for cloud. You will run out of battery way before you have a cooling problem. So the embedded development, how do you do this? So you write your code on your computer in your favorite editor, use some kind of compiler to compile the code into binary assembly code for the target device that runs the code and the application on the embedded IoT device. And then you use USB to push this into the device through an emulator that translates this into a serial communication that the target understands and is able to receive and program itself. And then once the target is programmed, you can start to run it. And then the emulator locally can halt it, can inspect regions of memory, can get trace data out from program flow, for example, and use that to display it back on the IDE of the PC. So this is how, even if you have no keyboard or screen on your actual end device, you use this little emulator to be able to use your computer as the keyboard and screen for debugging your IoT end device. So edge computing. This is it's one of those topics that gets talked about a lot. But I want to present my view. Other people have different views on this, but feel free to voice your opinion later. But this, the way we see it is radio transfers, sending data actually costs a lot of energy. And when you're in cellular, it doesn't only cost energy, it costs a subscription fee. Like you have a data plan. You don't want to use it all up or have to increase the data plan just because you were wasting how much data you're sending. So you should send information and not data. I'll give an example of what I mean by that. But that kind of falls apart when you were trying to learn something and improve your product or your algorithm, because then you actually need the data. You don't need the information. So when something interesting happens, you need to send the data anyway. So I'll walk you through an example, try and illustrate what I mean by that. But first I want to just show why why processing data is significantly cheaper than sending it. So this is an example from cellular IoT. If you're processing data on a typical like Cortex-M class processor, you're averaging around 3 milliamps of current over, let's say, 3 milliseconds. That should be ample time to do some simple processing on a couple of hundred bytes. If you want to transmit the couple of hundred bytes over the air through your cellular networks, instead of processing it locally, you're just sending it to the cloud. Then you're going to average about 150 milliamps over that pretty much same period of time. So this is why it's extremely important to transmit as little as possible, really distill the data down to information in the IoT device before you start sending it. So here's an example. So I pulled it off of this thing, which has an accelerometer on it. And basically, what we're looking at here is a time graph with the X, Y, and Z axis measuring basically gravity. That provides a continuous stream of 3 times 16-bit values, and it does so every 100 milliseconds. So you have the X, Y, and Z axis, 16-bit value on that, and it transmits it 10 times a second. And what you see is something happens here. Obviously triggering some kind of response from this device. It was probably sleeping, but then this happens, and then you get a response from the processor. It wakes up, starts to trying to digest what actually did happen, and if you do look for the information, you can see that what actually is happening here is this device is flipping over, changing which axis is up, and it's then after that laying flat. So this is an event. So instead of sending what is then, if you take this whole image, maybe it's like 100 bytes of data. You can actually get all that information into 1 byte of data, saying it flipped over to the left or to the right, and it's now laying still. That can be transmitted with 1 byte of data instead of sending all 100. But then something interesting happens. It's sitting there, as it should, and it wakes up because something's happening on the accelerometer. But it can't understand what happened. That doesn't look anything like the graph before. Right? The algorithm doesn't detect what is actually the event. So what do? You send the full data set that you have stored in your buffer, take it, send it to the cloud. You analyze by correlation to other known information that you hopefully have in your cloud. Well, let's say it's sitting on my desk in my office. What you'd probably find if you had access to the access control system is that at the very same time that this peak came out, someone actually opened the door. And just by the door closing, that was enough to trigger the little event. And that's the kind of magic you can do in the cloud. You can't do that locally on the device, but what you can do is you can understand that, and then you can make an algorithm that says, hey, if you see this thing, this is probably the door closing, so we'll categorize it as that, and then take appropriate action locally if necessary. Maybe turning off the lights, something like that. So this is why it's very important to, when there's something that happens that, if you have machine learning, you talk about the confidence level of the algorithm detecting actually what it is. This is when you have zero confidence, the algorithm is stupid, doesn't understand much, but when it understands nothing, it should just send the full data set up. And then I want to talk a little bit about expanding, because the cellular IoT is useful for a lot of different nodes, but there are certainly some nodes that are too small. Like you can't fit a cellular modem and the batteries and everything that's needed from an antenna perspective to deal with the sub 1 gigahertz. And then you may want to have smaller nodes, cheaper nodes, nodes that use less power and last for longer. You can do that, and then you build this sort of hybrid network. And a good example of this is the asset tracking. Again, going back to that container where you have boxes inside. So you track the container with cellular, and then you gather up the information using a local network to understand what actually is in that container. It's all of these different boxes, and then you transmit that back to the cloud over the cellular connection. And the boxes leave the container, go into a different container, that gets tracked over there. Continue to track them, but they don't all need to have a cellular connection. So you can mix and match a little bit and make a hybrid network that meets the requirements for power and cost, even if it still stays fully connected to the internet most of the time. Okay. So this is my last slide. I want to show you a little bit of summary, things that I want you to take away from this. So cellular IoT, it gives ubiquitous, low power cloud access to things. I mean, there's coverage virtually anywhere in most countries now that are developed, big cities at least. And over time, it will be almost everywhere. And then you can get connectivity for low power devices wherever you go. As a rule of thumb, LTE-M is for mobile devices with sort of medium data requirements, whereas NB-IoT is for stationary devices with low data requirements or throughput. And you should send information in the IoT, not data, except when something interesting happens. Then you need to send the full data set. And of course, I found the solution to my snow shoveling problem. And I'm going to reach out to these guys, but I found lefthandrobotics.com make this robotic snowplow that just travels around and passes information up to the cloud about where it is and how deep the snow is and the conditions, etc. And you don't have to lift a finger. You can sit anywhere you want and monitor that thing driving around your neighborhood, cleaning everything up. So that's the future, and it uses cellular IoT. So thank you. Any questions, or you can just come up.
Did you bring the chip that you provide?
Yeah, I always have it with me.
Nice. Can you show it?
Yeah, it's this little thing. That's the processing, the cellular modem, GPS, and all the memory and the crystals and power management and things that are needed for that. So essentially, you just need the antenna, that thing, and the SIM card. This SIM card is from Telia, but Telenor works as well. And yeah, and get cloud connectivity sort of anywhere you go, and you can operate on a battery. And we have ways to sort of measure the power consumption over time, so you can track what battery lifetime you can expect out of it. So, yeah, it's exciting.
You produce it here in Norway?
No, it's we design it in the Nordics. I would say it's a lot of the cellular modem guys are from Finland, ex-Nokia guys. No surprise. The low power MCU guys are all in Trondheim. And then we manufacture it in Taiwan and China and Malaysia, and we sell mostly Bluetooth Low Energy chips today, and we ship about 1 million pieces a day. So yeah, so this is going to be at least as high volume as that eventually. Yeah, so I mean, the 3 lithium-ion batteries there are not picked on random. That's actually a pretty good setup for a cellular node of this type. 3,700 milliamp hours battery for something that sort of just stays connected and doesn't send that much data is very reasonable for 10 years. And it really, again, fully depends on how you do your application. If you decide to send everything up all the time, the battery's going to be gone in a week. Almost doesn't matter which battery you put on it. And that's why it's very important to sort of facilitate local processing and also facilitate making sure that you don't let the modem use up all the resources. That's tricky because your phone is designed very differently. If you don't get the connection, it will try and try and try and try until the battery's dead. And if you're making a smart meter, for example, you can't do that. You need to make sure that if it doesn't manage to send anything for a week, that's fine, but it shouldn't drain the battery that was dimensioned to be there for 20 years in that week just because it couldn't connect. So very different problems to handle, but the sort of predictability of battery life is something that's very extremely important to handle in the cellular IoT. Otherwise, any calculation you make will just be wasted.
So if you don't have any connection to the network and you store a lot of data in the application,
Yeah.
does it drain a lot of battery then when you have a lot of memory in RAM?
That's a good question. No, but actually, we're talking tens of nanoamps to store the data per, let's say, 32 kilobytes of data. So that doesn't drain the battery too much. It's much more significant that when you then decide to send, you send with a lot less overhead. For example, in LTE-M, if you send 150 bytes or 10 times 150 bytes, actually doesn't make that big of a difference. So if you manage to buffer up a lot of data and store it locally, and the timing of getting it to the cloud is not that important, you can send data much more efficiently than if you do just 1 byte at a time. That's just because of the cellular network. Again, lots of devices, you have to kind of say, okay, I'm going to talk now, and you get a slot, and then you transmit. And if you transmit a lot, or a little at that time, it doesn't really matter that much. Not like in BLE or other sort of short-range protocols. Yes?
What about 5G?
Yeah.
What's happening going forward?
So LTE-M and narrowband IoT will actually both be part of 5G. So 5G is about 3 different things. One is the low latency, one is the massive IoT, and the other one is the very high throughput. And these are 3 totally different vectors. And the massive IoT part of 5G is actually LTE-M and narrowband IoT. As with any other standard, it's going to evolve, get new features, better performance, and all this stuff. But it's the same standards that are being carried forward, both of them. So not just one. So that was an important decision that was made this year, actually.
So if you had to guess, in 5 years, you're using this LPWAN to do a firmware update of the baseband. What will be kind of the new features in 5 to 10 years?
I think there will be a lot around location assistance. There are nice features already today in cellular to triangulate time difference of arrival between different base stations of known position. So you can get a rough estimate of where you are, even when you don't have GPS coverage, like indoors. So I think that's one of the things we're looking forward to. And then obviously improvements on efficiency, being able to reduce overhead, transmit more data in a shorter amount of time. I think that's, apart from that, there are just physical limits to what you can do. And the spectrum efficiency of the modulations that are used is like nearing the theoretical limit. So I don't think we'll see very significant improvements on that, but it's more, more the protocol that there I think we'll see significant advances. So.
And when you program on this module,
Mm-hmm.
like, what kind of programming language do you use?
So it's C for embedded programming. There are, there were some talks even this week about using JavaScript, for example, MicroPython. There are certainly opportunities to work at a higher abstraction layer, but it all gets translated into C. And for debugging, sort of the IDEs that are in operation today generally have this assembly language and machine code translation to C. They've got that down. So you can step through lines of C code, and for most of the time you can see the variable, see the value of the variable that you created. But once you take it up another level of abstraction to like JavaScript or Python, it gets translated again, which means you probably lose even more of the information that you use for debugging. So the variables that you defined originally may not even be there anymore. And that makes debugging with these higher level abstraction languages significantly different on these embedded devices. So I would expect C is probably for the, let's say, professional developer. I would think plain C is going to be the preferred language for at least another 5 years or so till they got this figured out.
What about, like, since we are very concerned about the battery life,
Mm.
could it be like you should write these applications in assembler so that you could write really optimal applications that you can reduce the power consumption by very much?
Yeah.
Is that concept compared to the rest of the, when you communicate with the cellular network and so on?
Yeah, I would say certainly like for encryption, compression, very computationally heavy algorithms, even like doing FFTs on understanding if there's a peak or a spike in a value, when the sort of inner loops of these algorithms, you can generally you can save something by writing them in assembly. But on the other hand, if you are a really good friend of your preferred C compiler, you can also generally make it produce the assembly code that you want by writing the C code intelligently. So there's, I would say, in like professional use, there are very few times when we see that assembly code is used for optimization of code. I generally find that a good C compiler is significantly smarter than me in optimizations. Think of things that I didn't think of. So there's, I think we're at that level now. Yes?
Would the device acting as a gateway towards the BLE devices need to stay away the whole time?
Yeah, that's an excellent question. And that, I think, is because I listed actually 3 different protocols. Bluetooth, Zigbee, and Thread. And there's actually a difference in actually exactly that aspect, because in Bluetooth Low Energy, it doesn't. It has very strict time slots. BLE is a synchronized protocol, so the central in BLE that is sitting on the gateway can actually go to sleep in between events. Whereas in Zigbee, and actually in Thread, the gateway device, coordinator in the Zigbee network, for example, needs to stay awake and in receive the entire time, because these are asynchronous protocols. So it never knows when the next packet is going to come in from the end nodes. So then it needs to stay in receive mode, draws around 5 milliamps doing that. and that's continuous. Whereas in BLE, it can go to sleep, draw like 2 microamps, 1 microamp, and still wake up at the exact right time to take the next connection event. Okay, I think we're out of questions. Thank you. Have a great weekend.